Welcome to the Macmillan Report. I'm Marilyn Wilkes, your host, and our guest is Priyamvada Natarajan, who is Professor of Astronomy and Physics at Yale. She is a theoretical astrophysicist interested in cosmology, gravitational lensing, and black hole physics. Her research and original contributions to the study of dark matter, dark energy, and black holes have won her many awards and honors, including election to the Fellowship of the American Physical Society and Guggenheim and Radcliffe Fellowships. Today we'll speak with Professor Natarajan about her book, Mapping the Heavens, the Radical Scientific Ideas That Reveal the Cosmos, which was awarded the Gustav Ranis International Book Prize by the Macmillan Center this year. Welcome, Professor Natarajan.
Thank you so much. So delighted to be here.
So let's talk about your book. I'm very excited. Let's start with an overview.
So the book chronicles the acceptance of radical scientific ideas in cosmology over the last 100 years. And the reason for choosing the past 100 years is that there have been very transformative ideas that have been proposed, new technologies that have enabled us to probe the cosmos better. And so I wanted to showcase how our cosmic understanding has so dramatically evolved, transforming our cosmic view as well as our place in the cosmos.
Mm-hmm. So what led you to write the book?
So, I've always been interested in writing because there is a process of clarification of ideas that happens even as a scientist when you write a scientific paper. And I also have a checkered history in the sense that I have an unfinished PhD in the history and philosophy of science. So I've always been interested in sort of the deeper processes by which we generate knowledge and how that knowledge gets tested and verified. And cosmology is a very interesting discipline. Mm-hmm. So it's one of those few disciplines where we cannot perform controlled experiments because, the cosmos is what it is. A supernova goes off here, you can't make it go off there tomorrow and make it repeat. Mm-hmm. So you have the cosmos and you can't perform any kind of controlled experiments. That's a challenge then to validate a theory or a model. Mm-hmm. And the solution that the field has arrived at is that you perform these very large-scale simulations. So simulations of a chunk of the universe, and you start off with a theoretical understanding, and you see how it evolves in time and see if any slice of it corresponds to slices that you actually observe in the universe. So I was interested in epistemically in this process of how you generate new knowledge in a field like cosmology where you can't do experiments. So that was what I was going to work on, right? So that has always been in the back of my mind. Mm-hmm. And so as my career progressed and I was working on these sort of forefront areas, and myself, I had these experiences of proposing new ideas and feeling the pushback and then eventually seeing how those ideas get accepted. It's really fortunate at this time, right, that in one lifetime of a scientist, you can actually propose an idea and mm-hmm. they can test it and it can be validated or invalidated. Mm-hmm. So during the course of my work, I realized that I have some interesting insights as an insider on this process and that I would like to share.
Okay. Let's talk about, you pick 8 or so of these transformational events or discoveries. So tell us about some of them and then talk about the process of them coming to be accepted.
So I think I start the book out with what I think was the most radical shift that happened, and that was the discovery of the expansion of the universe mm-hmm. by the astronomer Edwin Hubble. Till then, this is about early 1900s, so 1920, in the 1920s, and till then we believed that the cosmos was static, it was unchanging, and it was fixed. And his discovery of the expansion of the universe completely upended our notion. It was very disorienting discovery. Mm-hmm. And he used the speeds of nearby stars that he measured to infer this expansion history. And the process was complicated. Most astronomers found his evidence convincing and his argument. But Einstein, who actually had a theory of cosmology proposed, the theory of general relativity had been proposed, and it gave a very good description of the evolution of the cosmos, and so he did not like it because he was emotionally wedded to the idea of a fixed universe. So he pushed back. In fact, he went back and he tinkered with his equations to stop the universe from having a solution, an expanding solution. So in the book, I recount this tension and the back and forth, and Einstein desperately trying to recover a static universe and failing because the data was just starting to accumulate. And eventually, and this is what is so beautiful about science, right? Not only did Einstein change his mind, I mean, it was noted when he changed his mind. In a seminar, he finally said, okay, I believe this, right? He actually very promptly started working on the expanding model of the universe. So I wanted to sort of illustrate that whole circle. So you can have someone who's very skeptical, and that's part of having a scientific mind, but then when the data gets overwhelming, you have to change your mind, and then he starts working on it, trying to understand it at a deeper level. So that's one of the first ideas that I discuss in the book. And of course, rather close to my heart are this sort of subfields that I work in. So the idea of black holes.
Yes.
And the idea of black holes is really radical, and the reason for that is that no one believed they were actually real. They were actually mathematical solutions to Einstein's equation, once again. And so these are basically Einstein's equations tell you the relationship between matter and the shape of space. And black holes tend to be these very compact objects which have extremely pinch shape, shape of space. So they have a singularity, they have very peculiar mathematical property. Nobody thought that nature would actually produce such objects. So this would have to be objects that are so dense and so compact that the gravity around would be so intense that not even light can escape. So this was a mathematical idea. No one thought it was going to be real. Actually, the Indian astrophysicist Subramaniam Chandrasekhar worked out that the end state of very, very massive stars, when they die, they have a very explosive death. In the end, they leave behind this very, very compact object, which really looks like a black hole. That looks like the black hole solution. So once again, his very own mentor in Cambridge, Arthur Eddington, was a very established figure in astrophysics, did not like this solution and pushed back. And so, there was a very complicated emotional encounter, public encounter when they debated. And then, Chandra actually, Chandrasekhar is known as Chandra, actually left England, moved his entire career to the United States and settled down in Chicago. And it was not until World War II when people were actually able to, with the first computers, compute the problem of explosions, and they realized, in a different context of course, and they realized it's the same problem as stellar explosions, that they were able to arrive at this black hole solution. So, it took a long time, 30s to about 50s, that's sort of 20, 30 years before the possibility of black holes becoming real happened. However, the discovery of an actual object that had the properties of a black hole, especially supermassive black holes. These are black holes that are about 1 million times the mass of the sun, like the one lurking silently in the center of our own galaxy, the Milky Way. And these black holes, when they're actively growing, are glowing because of the gas that is falling into the black hole. The black hole itself doesn't produce light, because it actually absorbs any and all the light that strays nearby, but gas that is getting sucked in by the black hole, the dying gasps, the gas is glowing. And so you detect these objects as quasars. And the first quasars, these are sort of cosmic beacons, very, very bright, and they were detected in the 1960s. So it took almost 30, 40 years for this idea to be accepted, and it's one of the strange ideas, because it started life not as a physical object, but a mathematical entity. And then you were able to go and find the corresponding physical object that had those properties. And then the other idea, again related to the field that I work in, is dark matter, which is sort of different, where dark matter was detected observationally. We did not have a theoretical framework or any mathematical description.
What's the difference between dark matter and a black hole?
So a dark matter is gravitating matter that is present everywhere in the universe. It's smeared lightly pretty much everywhere, like jam on toast, everywhere in the universe. But there are regions in the universe where it's really lumped, and it's lumped around where you have light. So galaxies. So galaxies appear to have, from the evidence that we have so far, extended distributions of dark matter that go well beyond the light in the stars that we see. So black holes are extremely compact objects. We don't know what dark matter is made of, but whatever it is made of allows it to be spread out everywhere. Whereas black holes are really compact and they sink to the centers of galaxies.
Wow, that's fascinating. I'm curious to know how you did your research for the book, and actually how you went about choosing the 8 or so discoveries that you did.
So I think that the shape of the book evolved over time. So one of the sort of enduring interests that I've had since I was a young girl is maps. And this idea of mapping and this relationship of between mapping and knowing, when we can map something, the fact that we know it. And so originally I thought I would, because my own research work involves mapping this dark matter that is smeared everywhere from the deflection and the impact on light that this dark matter produces, this phenomenon of gravitational lensing. And I thought I would be writing a book that would be much more focused on mapping. But then I realized, and in all these radical ideas that I talked about, they're all centered around mapping. They all centered around observing, because astronomy is such a visual, observationally driven science that they all had aspects of mapping on them, right? I mean, sort of very part and parcel of the idea. So I think picking these 8 ideas was actually not difficult at all.
Okay.
I think there's enormous scientific consensus in our community that these have been the most impactful, radical ideas that have transformed our cosmic perspective.
And then how did you go about basically doing the research around each of them? I mean, because, when I read the part about Einstein finally acquiescing and saying, okay, it looks like you are right about this, and Hubble sounds like just such a fascinating individual. How did you do the research around all of the people in the book?
So because, I am interested in the psychology of science, I tend to read a lot about scientific memoirs as well as biographies and autobiographies. So, over the years I was reading, and I had sort of, made a note of these interesting individuals that, so when I sat down to write the book, there were a lot of sources. And there's also, it's a very rich genre. So a lot of astronomers and astrophysicists are writing books. Lots of science writers have written excellent books as well. So there were many, many sources, but I tried, for every chapter, I tried to find a couple of really original sources. So I dug into archives, and what is very fortunate today, right? You can be an armchair archivist. Everything is scanned, everything pretty much is available online. But, I made sure that other than the secondary sources that I used, that I always dug and looked for something new, particularly about the people and the controversies, and really about trying to read letters. So I read a lot of letters to try and understand the, sort of untangle the intellectual part of the controversies from the personal ambition, from all the other emotional human things that were tied into it.
Sure.
So I really wanted to write a book that was very different in this way from all the other books that are there. It's not entirely focused on the personalities, but the human side of the personalities and the intellectual work of those personalities is really there. And of course the technologies. So I am also interested, as I said, in the history of science and technology. So the history of the evolution of astrophotography and computing, and how that sort of has really helped the growth. It has really impacted. They've not been just mere tools. They've been more than tools. So they've been very intricately wrapped in with the ideas itself, because they actually help you forge new directions for exploration. So I think looking at archives, letters, and secondary sources. And of course, one of the things that I do is for each of these ideas, I try to bring the reader up to date to today. So I give you a status update. And that was, easy to do because I'm really active in the field, and that was a real fun and joy to write. And I really enjoyed that process of starting sort of historically and sort of having a non-linear narrative, and yet coming full circle and showing where we are today and how we got there.
When you were doing the archive work and reading the letters and trying to find new pieces of information, did you come across anything that said, hey, wow, I didn't know this, or kind of surprised you?
I think the thing that was most surprising to me was the discovery of a map. I thought I was really, I knew my maps. And in particular, I was interested both in celestial and terrestrial maps. So I think what was really surprising for me was this find of a map by Abraham Cresques. He was a Catalan, 13th, 14th century. And what was interesting about that map of the cosmos, obviously this was imagined cosmos. So it was a little bit of observational data. It was all naked eye astronomy, of course, at that point. And then there was a lot of myth. There was a lot of imagination, rich imagination.
What time period are we talking?
1300, 1400. And just the stunning rendition of this map in colors. And there was a major shift in his maps compared to maps from even 50 years before. And the shift was that there was an astrolabe in the center of the map rather than a godly figure. So, without reading too much into it, I think that there was a way in which he was able to see, or he captured sort of the potential of what instruments were going to do and the role that they would play in sort of transforming this map. So that was for me an amazing find because it encoded an intellectual shift of perspective that was subtle but very impactful.
Pretty visionary for the time, I would imagine. Yeah. So as a scientist, you are basically exploring the final frontier, being space. So I'm curious to know if there's something that you could discover, what would you hope it to be?
Well, as just after finishing to tell you that, scientists are obviously emotionally attached to their ideas. They shouldn't be, but try not to be. So I think there are two things. One is in the very near term, and one is slightly longer term that I would love to see detected and discovered in the cosmos, because I've kind of worked on this. One is, I worked on a potential new way to make the first black holes. So traditionally, black holes are expected, tiny black holes are left as remnants of stars. But they're too tiny to really explain how they could account for these supermassive black holes that inhabit the centers of most, if not all, galaxies. And we believe that these black holes could have formed, need to have formed very, very early on in the universe, because we are detecting these quasars that are powered by these supermassive black holes further and further back in time. And so the black holes that power these are about 1 billion times the mass of the sun. And you need such a big black hole to have formed when very few large galaxies have formed, right? So very few massive things in the universe have formed. And so we proposed this channel to form the first black holes, which is called direct collapse black holes, in which you bypass the formation of a star and a lot of gas just condenses. It's rather like the vortex when you pull the plug in your bathtub, the way the water rushes in. Something similar to that happens in the very early universe with gas. and gas gets funneled in and forms a black hole. So this picture, this idea we proposed it about 15 years ago, and we've been working on it, developing it, and providing observational signatures, calculating them. And the James Webb Space Telescope, which was due to fly this month and has been delayed for 2 years, is poised to discover them if they're out there. Mm-hmm. So I think in the near term, in the next 2 to 3 years, when this telescope flies, I would be thrilled if these objects were discovered. Uh-huh. Of course, I mean, it would be great either way, but I would be really thrilled if these red collapsed black holes are actually found. And I think that they have very clear signatures, and so we will be able to discriminate them if we find them. Okay. So that's the near term. And the longer term is, of course, the collisions of stellar mass black holes, these tiny black holes, was discovered by the LIGO collaboration. So the sort of earthquakes in space time that were detected, gravitational waves were detected by the LIGO collaboration. They were awarded the Nobel Prize last year. But these are the little cousins of the black holes that I really like, the supermassive ones. They also collide in the universe. And to detect the waves, the gravitational waves that are produced due to their collision, you actually need the kind of apparatus you had on the ground here in space. So that's another space telescope called LISA. It's a project I'm involved in on the NASA LISA team. And that, is proposed to fly in the 2030s. And they will discover, so this instrument will discover the first gravitational wave output from colliding supermassive black holes. I would love to see that. I've worked on various aspects of, what else you could see along with the gravitational waves from these black holes. So, and of course, there's always this big open question, right? The nature of dark matter. Right, it would be awesome if there was some discovery of the particle, some hint, even a small hint of what that particle might be, because we know so much about how the dark matter is distributed, how it clumps, and how it evolves over time, and it's in the driving seat of everything we know in cosmology, but the particle remains elusive. So that would be a very nice discovery. I always say maybe the next 5 years, and I think we have to be optimistic, because with science, you never know. You can never predict the future course of science, right? I mean, this team, the LIGO team that detected gravitational waves, the first detection, they'd been working for 40 years, right? So let's hope it's not another 40 years, but which would be pushing it for me. But it would be fabulous if these three things got found, illuminated, understood in my lifetime.
Right. Well, this has been fascinating for me. Thank you so much for being here today and sharing your work.
Thank you so much for having me.
For more information about Professor Natarajan and her research, please visit our website at macmillanreport.yale.edu. Be sure to join us again for another episode of the Macmillan Report, made possible through funding from the Whitney and Betty Macmillan Center for International and Area Studies at Yale.